Hello, my name is Shubham Kohli, and today I'm here to present you my machine learning classification project from Alma Better, which is mobile price range prediction. This is my individual project, and this is our project summary. The mobile phone industry is highly competitive, and the price of a mobile phone is determined by various factors, including battery power, Bluetooth, camera quality, screen size, and more. In this context, a study was conducted to understand the factors influencing the price range of mobile phones. The study used a dataset containing around 21 variables to predict the price range of mobile phones, categorized as low, medium, high, and very high. So at first, I have did some data wrangling, and after that, I performed exploratory data analysis. And after the EDA, I performed hypothesis testing, and after that, I have performed feature engineering, and also I implemented some machine learning models like logistic regression, random forest, and XGBoost. So this is my GitHub link, and this is our problem statement. In the competitive mobile phone market, companies want to understand sales data of mobile phones and factors which drive the prices. The objective is to find out some relation between features of a mobile phone, example RAM, internal memory, etc., and its selling price. In this problem, we do not have to predict the actual price, but a price range indicating how high the price is. So these are some general guidelines for our project. Let's begin. So at first, we will import some libraries, NumPy, Pandas, Matplotlib, and we use sklearn library in this project. And after that, we have to load the data set. At first, we will mount the drive. And after that, we will load mobile data CSV file. And this is our data set first view. So by dot head, we are able to see the top 5 rows. By dot tail, we are able to see the bottom 5 rows. These are the rows and columns count. We have 2000 rows with 21 columns. This is our dataset information. So these are the columns we have, and these are the data types. So we have 2 float and 19 integers data type in our dataset. So these all are not null, as we can see here, and we will check for the duplicate values. So we have 0 number of duplicate values in our dataset. Checking for missing or null values. So here we can see we have 0 number of missing or null values in our dataset. Now we will visualize a heat map to check the missing values. So here, as we can see, there is no yellow line, which means that there is no null value. So what did we know about our dataset? So our dataset contains 21 columns with 2000 rows. No duplicate and missing value is present in our dataset. Now, understanding our variables. So here we will check on the columns we have. So we have battery power, blue, clock speed, dual SIM, and so on. Now we will check the length of our columns, which is 21. Now by dot describe method, we will able to see the statistical information of our dataset, count, mean, standard deviation, minimum, maximum. So here we can see. And for variable description, here the battery power means the total energy a battery can store in one time measured in milliampere hour. And blue is Bluetooth or not. Clock speed is speed at which microprocessor executes instructions, and so on. Here we can see we have screen height, screen width, talk time, 3G Wi-Fi, and so on. Now we will check the unique values for our each variable. So this is the detailed description, and here we can see the count of our unique values. Like battery power, we have 1094, and Bluetooth we have 2 values, and so on. Now we will do some data wrangling. So the minimum value of pixel height and screen width should not be 0, as it does not make any sense for a phone screen width or pixel height to be 0. So therefore, we should check for and handle these cases appropriately to avoid any issues with our analysis. So at first, we will check the number of phones which with the screen width 0. So they are 180, and number of phones with pixel height 0, they are 2. So we will replace the 0 values with mean value. So after updating our data frame, here we can see the screen width, these 2 columns, screen width and pixel height. So you can see these are the updated data set. And now checking whether there is duplicate value or not. So we have 0 number of duplicate values and 0 number of null values. So what all manipulations we have done and what insights we have found. So we have found that the number of phones with pixel resolution, height, and screen width of mobile in centimeter are 180 and 2 respectively, as we have seen above. The minimum value of pixel height and screen width should not be 0, as it does not make any sense for a phone screen width or pixel height to be 0. Therefore, we should check for and handle these cases appropriately to avoid any issues with our analysis. So the 0 values are replaced with the mean values and no missing values left in the table. So our data is ready for the analysis. Now for data visualization, this is the chart first we have for price range. And here, as we can see, all categories of phone are distributed with equal price range. For 0, 1, 2, and 3, they all have 25% distribution. And the insights we have gained are, yes, we are able to know distribution of phones in percentage. So we have information about distributions. So the next chart is for battery power, as we have created a disk plot here. And this is the battery power, and these are the counts. So this plot visualizes how the battery capacity measured in milliampere hour is distributed across the dataset. We can observe that the distribution of battery capacity is positively correlated with the price range of the mobile phones, as there is a gradual increase in the battery capacity as the price range increases. So the insight we have found from analyzing the relationship between the battery capacity and the price of a mobile phone can potentially lead to a positive business impact. Next chart is for Bluetooth. So we have seen that almost half of the devices have Bluetooth and half don't have. Zero is they don't have any Bluetooth in their phone, and one is they have Bluetooth. So here they are equally distributed almost. And the insights we have gained that the observation that almost half of the devices in the dataset have Bluetooth and half do not could have a positive business impact if a company can leverage this information to improve its products or marketing strategies. Our next chart is for the RAM. And here, these are the price range 0, 1, 2, and 3. And this is the capacity of RAM. So here we can see this scatter plot shows a clear positive correlation between RAM and the price range, with the majority of the data points clustering towards the upper right corner. As we can see, the third number has the highest value of RAM, and the zero price range has the lowest value of RAM. So the insights gained from the scatter plot, such as the positive correlation between RAM and price range, can be valuable for business. Our next chart is for dual SIM. So these are the new number of dual SIM devices by price range. So we can observe that up to low, medium, and high, almost it is same. But for very high price range, it is seen that it is found that the count is raised who's using dual devices, and count is increasing for dual devices. And the insights we have gained is it is very useful because we can identify dual SIM is actually increasing count or not. So our next chart is for 4G. Here we will check the percentage of 4G SIM devices in price range 0, 1, 2, and 3. So here we can see 48.2% phones does not contain 4G in the price range 0, and 51% contains 4G. So here we have found that at low, medium, and very high prices, the mobile phones having SIM in more number, but in high price, it is showing slightly collapse. So here we can see now the insights gained from the analysis of the number of SIM cards in mobile phones at different price ranges can be helpful in creating a positive business impact. Now for pixel width. So here pixel width distribution by price ranges. So here the violet color is for 0, the blue color is for 1, this one, the green is for 2, and the yellow is for 3. So here we can see the pixel width from 500 to 1000. There is a maximum density for the 0, and for 1500 to 2000 pixel width, the maximum density is for 3. And here we have created a box plot too. And here we can see it has the highest number of pixel width, and 0 has the lowest number of pixel width among them. And we do here we can see pixel height distribution by price ranges. So from 0 to 500, the density is the highest for the zeroth number, and density is lowest for the 3 number, which is yellow. And here the box plot we can see. So based on the analysis on the pixel width distribution across different price ranges, it can be observed that there is not a continuous increase in pixel width as we move from low cost to very high cost mobile phones. So the insights gained from the analysis of pixel height distribution across different price ranges can help create a positive business impact by providing useful information to mobile phone manufacturers and marketers. Now we will check for the front camera megapixels. And here it is almost same impact of price ranges in all categories. They are almost same. And the observation that the distribution of front camera megapixel is similar across all price ranges suggests that this feature alone may not be help predictor of price range. Now, next, we will check for primary camera megapixels. And here we can see the number of cores versus density. So for 0, this is the line. Now, this is the number of cores, and the black one is for number 3. We have also plotted a box plot for price range up to number of cores. And the distribution of primary camera megapixel across different target categories is relatively consistent, indicating that this feature may not significantly influence the price range of mobile phones. So the gain insight can help create a positive business impact by providing an understanding of the relationship between different features and the price range of mobile phones. Now we'll check for the mobile weight. And here, these are the price ranges, and this is the density. So for 0, as we can see here, for 175 to 200, and in between 75 to 100, this is quite high. And this, we have also made a box plot for price range to mobile weight. And here it can be observed that mobile phones with higher price ranges tends to be lighter in weight compared to low price range phones. So here, as we can see, the price range 3 has the lowest weight among them, and the price range 0 has the highest weight among them. So the gained insight from the analysis can be definitely help to create a positive business impact. Now we'll check for the screen size. So at first we can convert the screen size variable from centimeters to inches to align with real life usage, as screen sizes are typically communicated in inches. So here we have changed the screen size into centimeter, from centimeter to inches. And after that, here we can see the screen size inches to density and price range to screen size inches. So they are almost equal. So the analysis of the screen size distribution among different target categories indicates that there is not a significant difference in the distribution, suggesting that screen size may not be the sole driving factor in determining the target categories. The gain insight from the analysis of various features of mobile phones can have a positive impact on business. Now we will check for 3G. So percentage of 3G SIM devices in price range is 0. So here in price range 0, no 3G phones have 25.4% and 3G phones have 74.6%, as we can see here in price range 2, 3, and 1. So we have found that 3G SIMs are present more in the percentage in all price range. And the insights that 3G SIMs are present more in all price range could potentially have a positive business impact for companies that manufacture or sell mobile devices. Now we'll check for the Wi-Fi. And here we can see the Wi-Fi availability is 75% and unavailability of Wi-Fi is 25%. So the insights gained from the visualization can help in creating a positive business impact by providing information about the availability of Wi-Fi in different price ranges. Now we will build a correlation heat map. And here, as we can see, the price range and RAM has a very high correlation, and screen height and screen size also have a very high positive correlation. So the high correlation between RAM and price range is a positive sign for businesses, as it indicates that RAM will be a major deciding factor in estimating the price range of a mobile phone. Now we will do some hypothesis testing. So our first statement is all category phones are distributed with equal range. So our null hypothesis will be all categories of phone are distributed with equal range, and our alternative hypothesis will be all categories of phones are not distributed with equal price range. So we will perform an appropriate statistical test. Here we have imported pandas as from SciPy. We import stats, and our chi-square statistic value is 0.0 and p-value is 1.0. And our second statement is around in 25%, the Wi-Fi is not available, and in 75%, the Wi-Fi is available. So our null hypothesis will be the proportion of times when Wi-Fi is not available is equal to or less than 0.25. And the proportion of times when the Wi-Fi is available is equal to or greater than 0.75. Our alternative hypothesis will be the proportion of times when Wi-Fi is not available is greater than 0.25, or the proportion of times when the Wi-Fi is available is less than 0.7. So again, we will perform an appropriate statistical test. So this is our test. And here it has failed to reject the null hypothesis. A test static value is 0.0 and p-value is 1.0. So the statistical test that was used to obtain the p-value is one sample proportion test. Our third statement is I have found that the 3G SIMs are present more in percentage in all price ranges. So our null hypothesis will be the proportion of devices with 3G SIMs is the same across all price ranges. Our alternative hypothesis will be the proportion of devices with 3G SIMs is different across at least one pair of price ranges. Again, we will perform an appropriate statistical test. Here, the price range is 0, 1, 2, and 3. So the 3G SIM, this is the count for 3G SIMs with for phones which do not contain. So, and these one is the count that the phone contains, the 3G SIM. So our chi-square statistic value is 1.37 and p-value is 0.71. So the statistical test I used to obtain the p-value was the chi-square test of independence. And now we will do some feature engineering and data pre-processing. At first, we will handle missing values. So here, as we can see, we have no missing value available here. And we'll check the outliers. And these are the columns we have. So there are no outlier here. As we can see, this is the outlier, but we can ignore it. So there is not much outlier are present. No need to do that much experiment. And we'll check out categorical coding. But categorical coding is not necessary because all values are present in integer or float. Now we'll do some data transformation. So here we have dropped pixel height and pixel width as they are not any of any use. Now we'll do some data scaling. From sklearn pre-processing, we have imported min-max scaler. So the code is using min-max scaler from scikit-learn library to scale the data in X. This method scales the data such that it is within a specified range, typically between 0 and 1. Now we'll do data splitting. So we have defined X and Y. So we have X, which is of 2000 rows with 19 columns, as we have earlier 21 columns, but we have dropped these 2 columns. So we got 19 columns here. And in Y, we have 2000 rows. Now splitting dataset into train and test. So from sklearn.model selection, we have imported train test split. We have xtrain, xtest, ytrain, ytest, and train test split function. Here we have test size 0.20, which means 20%. So our rest of the data, 80% will be the training set. And in our training set, we have 1600 rows with 19 columns, and ytrain, we have 1600 rows. After that, we will do model implementation. So our first model is logistic regression. From sklearn linear model, we have imported the logistic regression. And here we have classification report for logistic regression for test set. So we have precision, recall, and F1 score for 0, 1, 2, and 3 price ranges. For 0, the precision score is 91%, and recall is 90%, and for F1, it is 91%, and so on. And we have macro average, which is 78 and 79%, weighted average, which is 79%. We have also created a confusion matrix. So for 0, it has predicted 96 values correctly and 9 values incorrectly. And for 1, it has predicted 63 values correctly and 11 and 17 incorrectly, and here so on. Now evaluation metrics for training set. So this is our classification report for training set. So for 0, 93 is precision score, 88 is for recall score, and 90 is for F1 score. And for macro average, the 83% is average, and weighted average is 84 and 83%. So now we will do some cross-validation and hyperparameter tuning. So our cross-validation score is this, and we have the average cross-validation score, which is 81% we have. So the best cross-validation score is 82%, and best parameters are C is to 10. The test score is our 82%. So we have used grid search CV, which is a commonly used technique for hyperparameter tuning that involves searching over a predefined graph of hyperparameters and selecting the combination that gives the best performance on a validation set. So the best cross-validation score achieved was 0.82, and the best hyperparameter value for C was found to be 10. So these are the evaluation metric for explanation, precision, recall, F1 score. Now our next model is XGBoost. So from XGBoost, we have imported XGB classifier, and this is our classification report for test set. So for 0, we have 91% is precision score, 91% is recall, and 91 F1 score, and 77 for all these for 1. Now macro average, which is 81 and 80% we have, and weighted average is 82 and 81%. Now we'll see the classification report for train set. So for 0, it is 99% for precision and 100% for recall and 99% for F1. And macro average is 99% and weighted average is also 99%. So XGBoost model on the training set, it achieved a very high accuracy score of 99%. So it is important to also evaluate the model's performance on the test set to ensure that it is not overfitting to the training's data. Now we'll do cross-validation and hyperparameter tuning. So this is the best hyperparameters we have, and cross-validation score is 81% we have. And classification report for test set is for 0, it is 91%. For recall, it's 93%. And F1 score is 92%. And our macro average is 80% and weighted average is 81%. And we have also created a confusion matrix. So it has predicted 98 values correctly and 7 incorrectly, 69 correctly, and 10 and 12 incorrectly for 1, and so on. So we have classification report for training set. So for 0, it has precision score 99%. For recall, it's 100%. And for F1, it's 99. Macro average is 99 and weighted average is also 99. So here I've again used the grid search CV. And our third model is random model classifier. So we have taken so from sklearn.ensemble, we have imported random forest classifier. We have taken 300 trees in our random forest. So our test score is 80% and train score is 100% in our dataset. Now classification report for test set. For 0, we have precision score 91 and 95% for recall and 93% for F1 score. Our macro average is 81 and 80%, weighted average is 81%. This is for test set. And we have created a confusion matrix. So it has predicted 100 values correctly, as we can see here, and 5 values incorrectly, 68 correctly for 1, and 10 and 13 incorrectly, and so on. Now, after that, I've stored these values, these features in a feature importance variable. At first, I have sorted these scores, and after that, I created a bar plot, and here we can see the RAM has the highest value. After that, battery power and mobile weight, and last, the least value is for 3G and 4G. So this model used as a random forest classifier. And now cross-validation and hyperparameter tuning. So here, so we have best score is 80%, and we have created a confusion matrix. So it has also predicted 100 values correctly and 5 incorrectly, 68 correctly and 10 and 13 incorrectly, and so on. Now we'll do the train test split. The accuracy of our score for training set is 90%. And here, the precision value for training set is 91% for 0, 97 recall, and 94 for F1 score. Macro average is 90, 91, and 90. Weighted average is 90%. For test set, we have scored 80%, and these are the scores for precision recall and F1 score. And again, I have stored these values in feature store, feature importance. Again, I sorted, and again, we have got the RAM as the most number of the RAM scored the most, and then battery power, then mobile weight, and these Wi-Fi dual SIM has a negligible values. So I have again used the grid search CV. Grid search CV is a commonly used technique for hyperparameter tuning. It performs an exhaustive search over specified hyperparameters values for an estimator and evaluates each combination using cross-validation. So yes, there is an improvement in overall performance of the model. The accuracy has increased from 0.80 to 81, and the weighted average F1 score has also increased from 0.80 to 0.81. So we have question like, which evaluation metrics did you consider for a positive business impact? So we have considered weighted average for precision recall and F1 score, macro average for precision recall and F1 score, and confusion matrix. And these are the details why we have used it. And our next question is, which ML model did you choose? So I've choose logistic regression and XGBoost model because they predict better results than the random forest regression. So now explain the model which you have used for the feature importance using any model explainability tool. So I can explain the logistic regression and XGBoost models and feature importance using a model explainability tool. So logistic regression is a linear classification algorithm that models the probability of a binary outcome as a function of the input features. XGBoost, on the other hand, is a powerful tree-based ensemble learning algorithm that uses a series of decision trees to make predictions. To explain the feature importance of the logistic regression and XGBoost models, we can use the SHAP, which is Shapley Additive Explanation Model Explainability Tool. So now we have conclusion. So the EDA revealed that the dataset consists of mobile phones grouped into 4 price ranges with similar number of devices in each range and a 50-50 distribution of Bluetooth. We also observed that RAM and battery power increase with the price range, and higher priced phones tend to be lighter. Our experiment suggests that the most important factors affecting the price range of mobile phones are RAM, battery power, and pixel quality. Finally, we found the logistic regression and XGBoost algorithm, coupled with hyperparameter tuning, provide the best performance in predicting the price range of mobile phones. Thank you.